So thank you, Florian and Micha, for the kind invitation and for believing I can be a tutor for this school. So my topic is laser cooling of neutral atoms from atom-light interaction to optical lattice clock. My lecture was supposed to be divided in two parts, and I will try to use like the formalism of the first quantization. There is plenty of theoretician maybe later in the school to give you the real taste of what is the quantum electrodynamics from the quantum point of view. So I will start with an introduction of laser cooling, and then a little bit of reminder of what is the atom-light interaction, and then we will go through the hard mathematics of the radiative forces on two-level atoms. And then I will stop, and probably you will have, I hope, some questions. And I hope you find all my typos. I couldn't go through all the slides. In the second lecture, I will just briefly remind the technical part of how we use this theory for cooling and trapping ultra-cold atoms and make then the most precise clocks in the world. So what is the original motivation and the most practical use for having ultra-cold atoms? And the answer is very easy: atomic clocks. This is why there is a lot of shift due to the emotional effects. The first order Doppler is very, very disastrous for a thermal atomic beam. If you take 100 meters per second, you get something like 10 to the minus 6, which is unusable. So you need to develop some Doppler-free techniques, but at some point you still have to get rid of this problem. And the second is the second order Doppler cooling, and this is quadratic with the velocity, and there is no way you use a Doppler-free to cancel this effect. This has to be measured, and for instance, for the old cesium beam clocks was of the order of 10 to the 13. That's why at the middle of the 70s, two different groups, one with the aim of clocks and the other one with the aim of ultra-precise measurement, for instance, for the hydrogen spectrum, start to think about how we can cool atoms. This is a little bit of this fantastic and successful journey. In 1917, so Hensch and Shallow with Weinand and Demelt make the first proposals. Then there was the first demonstration actually with trapped ions. At the end, in the group of Bill Phillips, who got the Nobel Prize, finally demonstrated the use of light to cool down a thermal beam. Then this technique was extended to 3D cooling by Stephen Chu, another Nobel Prize. And then there was the theory of magneto-optical trap by Dalibard and Cohen-Tanguy, another Nobel Prize. So it's full of Nobel Prizes, and it's nice to collect all of them, even if these two guys got the Nobel Prize not for directly laser cooling. And the maximum achievement was, of course, in 1995, when laser cooling reached so low temperature that we observed for the first time the quantum statistics applied to gas of ultra-cold atoms in the group of Eric Cornell and Catterley. So this is quite actually the past, but now we have done a lot of a long road. So we use now laser cooling for to exploit matter-wave duality. We can make with ultra-cold atoms the best inertial sensing up to now. We have very good gravimeters and gradiometers. Actually, we are able to measure now the constant the gravitational constant almost with the same precision of the codata. Also, it is used for, since the creation of the first BEC, to explore new quantum states of matter, but also it is a very promising research area is the quantum simulation, and also quantum simulation and metrology. Since we are still working with clocks, we are very, very interested on exploiting ultra-cold atoms and take full advantage of the quantum technologies. Using light to cool atoms seems quite a intuitive idea. I mean, in our experience, when we have light on us, we just feel warm. We don't feel cold at all. That's because atoms actually don't absorb light. They scatter photons. And the scattering process actually preserves the momentum. So in principle, and we can also exploit the fact that the emission is spontaneous and isotropic. So we can think about a cycle in which we have a moving atom that meets a counter-propagating photon. This absorbs the momentum of the photon, so the momentum is reduced by this amount. Then it releases by spontaneous emission isotropically. So on average, this delta P, this momentum change is almost zero and cycles many, many, many times. And we can make some order of magnitude calculation. This is what physicists always do. So if we look at the change of velocity in time, this is proportional to the number, to the average number of recoil cycles times the recoil velocity due to the absorption of the photon. And this is proportional also to the scattering rate and the photon momentum divided by the mass. From this, we can extrapolate like a sort of semi-classical force, which is the product of the mass and the change of the velocity. And the force that we can get is proportional to h bar KL gamma. So the change of, so this is a very, very strong force. If we take, for example, the strontium atom with a transition of about 30 megahertz at a wavelength of 461 nanometer, the force that we can expect is 10 to the 5 times more than its gravitational attraction. So one may wonder why we didn't use earlier before this technique. Also, we can estimate what is the energy, the ultimate energy that we can achieve with this cycling of cycles of absorption and emission. Of course, there is an indetermination of the energy of the emitted photons due to the scattering process, which is proportional so to the gamma, the scattering rate, the spontaneous emission rate. And we can, let's say, make this equation. Here, there is no equal, of course. And we can extract a limiting temperature, which is proportional, of course, to h bar gamma over kappa b. So from these very simple arguments, we already got the limit, more or less, of Doppler cooling. So the next slides, which are very heavy, we'll try to see if this is a correct guess and how much is wrong. So as I said, there are two main ingredients to make laser cooling of atoms with light. We need a fast cycling transition, so this has to be repeated several times until you get proximus to zero velocity. And the second is you need an intense monochromatic light source. That was the ingredient that at the beginning of the quantum revolution the physicists missed. The lasers were available just from the late 60s. Okay, this is the mathematical part. We consider the Hamiltonian of an atom just considering its kinetic energy. We consider also the nucleus at rest. So this is basically the momentum of the, is the reduced momentum, but it's basically the momentum of the free electron, plus an interaction, internal potential, which, as we know, for instance, for the hydrogen atom, gives rise to several quantized energy levels. Then we apply, in the semi-classical approximation, the standard Hamiltonian for the interaction of light with matter. So we have to change the momentum with this, applying also the electromagnetic potential and also adding a static electric field. And this gets this formula in which I already used the Coulomb gauge. And there is this second term that we can drop because the interaction strength is, we consider, much less than the internal energy and energy structure. Also, we consider a monochromatic plane wave, so there is no electrostatic field. And the resulting Hamiltonian is this one, with a time-dependent cosine perturbation. So this is the, if we look back at a lecture of quantum mechanics, is the typical time-dependent perturbation is the Rabi problem. So we can think about solving in that way. So it's the same as for magnetic resonances or other similar problems. But we just don't like very much this to deal with the electromagnetic potential. So we need to look much more careful at the system, and we can see that we can make the approximation that for optical radiation, the wavelength of the radiation is much, much bigger than the typical dimension of the atom. So we can expand at least the spatial dependence of this of our monochromatic plane wave, and just take the first term. Then we change, of course, A0 with the amplitude of the electromagnetic field. This is something that we like and we measure, and we exploit this relationship for the commutator of the position operator, which is so we change the momentum operator with the position operator commutator with the Hamiltonian. If we make some a little bit of math, we can exploit these and apply the Fermi-Golden rule, and at the end we see that for this potential, the expectation value between two atomic eigenfunction is proportional to the energy separation divided by the frequency of the radiation times the electric dipole operator times of course, the amplitude of the electromagnetic field. This is typically 1 on resonance. So we see that we can approximate the atom-light interaction just with the Hamiltonian, with an electric dipole Hamiltonian. So what happens when a monochromatic light perturbs an atom? We look back at our full Hamiltonian, and in this time we express as a function of the atomic internal state eigenvalues. And this is a really big mess. I took from this book the energy structure of, for instance, strontium. So it's very difficult here to deal with all these energies. And these instead are the two operators that we consider. So there are a lot of states, and we cannot deal with them. So we make the assumption that the electromagnetic radiation has a bandwidth such that it is able to excite just one level, and just two levels are populated during the internal dynamics of the system. So this greatly simplifies all our Hamiltonians. So from a set of several states, we get just two states. It's a two-level system, and the dipole operator is very simple. It's an antisymmetric matrix, and the internal Hamiltonian is just I put the ground state at 0, so it's just the projection to the excited state. Then I do this substitution. I define the so-called Rabi frequency, that is function of the position of the center of mass, which is given by the scalar product of the dipole operator and the polarization operator. In this way, I greatly simplify my Hamiltonian. I took both these and these as real, and I put outside a spatial dependent phase, so that everything looks quite nice. We still have this not very nice cosine omega LT time dependence, but as we probably should know, there exists a unitary transformation for the rotating frame, and we take so we use actually the internal Hamiltonian, and we just take as energy as a frequency of the system rotating the frequency of the oscillating light. And with some not very difficult math, we get this very simple Hamiltonian. Okay, here we see two terms that are very simple to understand. So you can excite an atom absorbing a photon, or you can release a photon exciting the atom, is the other way around. And then we have these two terms at twice the frequency of our laser radiation, which are non-resonant for the system, so we can drop out them. And this is the very famous rotating wave approximation. So in the rotating wave approximation, of course, we have a system that is not more time dependent, so now the mathematics is much, much easier. So typically one solves quantum mechanical problems in the Schrödinger picture, but sometimes it's more useful to introduce the density matrix operator, which is a very general picture, and it can also be applied to statistical mixture, not just to pure states. So when we solve the equation for the density matrix, we get the so-called optical block equation that takes this quite very compact operational form. This Hamiltonian actually is the complete Hamiltonian, but we can see that for the internal state wave function, there is commutation with the external degrees of freedom of the Hamiltonian. So we just look back at the internal part of the Hamiltonian, and this is, if we do some math, what we get. We have 4 coupled differential equations. But we have to consider that by construction, the density matrix is both Hermitian, and the probability has to be conserved. So this means that there are only 2 independent equations with complex values, which actually reduce to 3 variables. And this is due to Feynman, another Nobel Prize. This is very nice representation of the problem, in which we recast again the elements of the density matrix so that U, V, and W, because at the time they didn't like X, Y, and Z, are real variables. And they look like the coordinates of a vector. In fact, all the dynamic of a 2-level system can be represented in a sphere, the so-called block sphere. So from the definition, it's easy to see that, for instance, the coordinate W is just the difference of the population of the 2 systems and lies on the Z axis. And the part of the Hamiltonian that is not due to the electromagnetic wave makes the system rotating around this vector. Instead, the part of the electromagnetic wave that changes the dynamics of the density matrix lays in this plane. At the end, we can construct so a vector, the omega vector, and the dynamics can be very compactified in this vectorial form of the optical block equations, in which the vector R precesses around the Q vector. So I already anticipated what is W. We want to know what is U and V from a physical point of view. And if we look at again back to the dipole operator, and we do his expectation, and we calculate his expectation value, that in the formalism of density matrix is the trace of this product, we see that at the end, we can write down as twice the dipole moment times U cosine omega t minus V sine omega LT, which means that the U coordinate is the one that is in phase with the impinging electromagnetic wave. Instead, because of this minus sign, the V coordinate is in quadrature with the evolution of the electromagnetic wave. And this has a very important consequence in the dynamics of the light-matter interaction that we will see in a minute. Do you have any questions? This is basically standard quantum mechanics. We don't even need to call it electromagnetic wave. Okay, here the thing gets a little bit more complicated, because actually, as we know, the electromagnetic field is quantized in many modes that are characterized by many infinite k vectors and the polarization vectors. And this is the typical Hamiltonian of the reservoir, that it is always on, even if it is, the mode is empty. In fact, if we take the vacuum state and we make the expectation value, for instance, of the electromagnetic field, we get 0, but its variance is not 0, and this has dramatic consequences. So in principle, when we have an atom that is excited, there is a finite probability that this will interact with the electromagnetic field, with the electromagnetic modes, and give one photon to one of these empty modes. And we can still use the Fermi golden rule, use this Hamiltonian, which is the same as the one I saw before, just for the Rabi frequency. We have to use the vacuum Rabi frequency. And this is the density of states, and here we can receive the very famous formula, which connects twice the momentum, the dipole moment, to the probability of spontaneous emission. So how we can integrate this problem in our dynamics? This is very simple. Typically, one add by hand to each term of the density matrix a decay term. So the excited state, the probability of to be in the excited state is minus gamma rho EE. And the same we do for the diagonal terms. Just is 1/2, because there is half a probability to be on the ground state and half in the excited state. Instead, for the ground state, we have a plus. So every time some photon decays, some atom decays, we have one more atom on the ground state. If we use the very famous Pauling matrices, and in particular their lowering and raising operators, we can write down this operational equation in this very quite compact form. But this doesn't matter. The point is that if we look back at our block vector, we need to add to the system this vector. So it means that when the atom evolves, it actually collapses at some point to 1/2. So the solution of the optical block equations with the decay terms is not very trivial. But in 1994, this story was able to find an analytical expression, and this is the parametric form of this of these solutions. But since the dynamics is very fast compared to the dynamics of the external degrees of freedom, we are more interested in calculating just the steady state values for the block vector. And these are the typical formulas. I'm not going through the calculation of these, just take it as it is, and if you don't believe, I will give you at the end some references. And we will express them as a function of this parameter S, which is actually the ratio, the on-resonance saturation parameter, so the intensity of the laser times the saturation intensity, which is defined in this way. If we look, for instance, to the steady state value of the W component, we see that for S that goes to infinity, this saturates to 1/2. And there is no way to do better than that. Okay, finally, we have all the ingredients to calculate how the interaction of light with matter influences the external degrees of freedom of our atoms, and how we can exploit them to control and cool probably the atom. Of course, we have to make some approximation. The first approximation is that we calculate the atom at a fixed position and at a fixed velocity. So these two values does not influence the internal degrees of freedom. And this is valid for, again, for in the long wavelength approximation. So if the extension of the wave function is much, much less than the wavelength of the radiation, and the same, the spread of the velocity is much, much smaller than the typical velocity of the problem. And if we recast these two inequalities and we use the Heisenberg uncertainty principle, we recover this so-called broadband condition. So the recoil frequency has to be much, much smaller than the spontaneous emission decay rate, which is quite typical for most of the atoms that we use for laser cooling, but is not always true. For instance, in strontium, there is at least one famous transition for laser cooling that does not satisfy at all these conditions. So you have to solve at the same time both the external and the internal degrees of freedom equation of motion. By the way, we can define a semi-classical force operator as of course, the derivative of the momentum operator that we can, of course, use in the Heisenberg picture using the Heisenberg equation. Of course, we use the commutation relation, and we see that the force is just the the divergence of the Hamiltonian. And in our case, is the divergence of the atom-light interaction, and because it commutes with P, and the divergence of the atom-reservoir interaction that we kept for a while. But since it is a semi-classical approximation, we are more interested not just on the operational function of this operator, but at its expectation value. So we can make the expectation values for 2, and we see suddenly that this drops out, because if there is just a vacuum field, this has averaged 0. For solving the this semi-classical equation, we have to make other approximation. So when we do this this derivative, we assume that the dipole moment is constant. So we don't differentiate inside mu. And the other is that we can solve independently the Bloch equation and the semi-classical equation for the external degrees of freedom. So we take back our Hamiltonian in the rotating wave approximation, and we make the trace with with our nice density matrix, keeping all the phase forms. So this is very complicated equation if we look at, but we have to exploit the approximation we said before. So we neglect the spatial variation of the electric field over the size of the atom. This means that we can take away from the trace the nabla operator. So we just do the trace of the totally antisymmetric dipole operator that is just proportional to the Rabi frequency, and we get this nice equation. And then we do the differentiation, and we get a term for the two coherences of the density matrix. So the internal degrees of freedom of the atom was a much shorter scale, as I said. So we use at this time. So in principle, this is a time-dependent equation. But this is, as I said, we are not very interested on the transient behavior of the atomic internal degrees of freedom. So we can change rho Eg with rho Eg stationary. And if we make the assumption, as I said before, that we are at position 0 and the phase is 0, the force nicely reduces to this very simple equation. So there is a term that is proportional to the gradient of the Rabi frequency, in which that, as I said, the spatial dependence is just the one of the amplitude of the electromagnetic wave. And a second term that is proportional to the gradient of the phase. And we see here, I solved the equation for the density matrix, but actually it takes a very, very compact form if we take back the Feynman representation of the block vector. So this term proportional to the gradient of the amplitude is proportional to the U standard stationary component of the block vector, and this second part is proportional to the V, so the in quadrature term of the of the block vector. And so we have two different forces. The first one that is proportional to the gradient of the amplitude of the electromagnetic field, we call it the reactive force. And the second one is the addissipative force. And now we see why we call it dissipative. Is straightforward? Okay. So if we look back, we take this VST formula, we plug into our solution for the force, and we get this nice result. So there is a first term, which is proportional to the, let's say, our indetermination energy. And there is this second factor, which is exactly multiplied by a factor 1/2, the steady state value of the differences of the populations, times the gradient of the phase. And if we consider the simplest case, so for a plane wave, the gradient is just a decay vector, we recover the force that we already mentioned at the beginning of our lecture. So the dissipative force is made by just the scattering rate of our atom times the momentum that we absorb, where the scattering rate takes this form and saturates to gamma half. So we did all these mathematics just to recover what we more or less already saw. We can go a little bit more in detail on this formula, which is very instructive. As I said, if we look its dependence on the saturation parameter, so on the intensity of the laser, it saturates to a maximum value quite quickly. Instead, the shape is a Lorentzian shape, and when we increase the saturation, there is a square root dependence on the width of the resonance. So the second component of our force instead is the so-called reactive force, which is proportional to the gradient of the Rabi frequency. And if you believe to some algebra, we can express as a function of the gradient of the saturation parameter. We see immediately that if we have a plane wave, there is no reactive force at all. So this disappears completely. But we can take a second typical example. So we take a standing wave, so two counterpropagating waves. In this way, we have an explicit dependence on the space. We make our nice differentiation. And again, we recover this formula and a periodic dependence on the space. So if we look at this formula, we can actually derive it from a potential, and that's why we call it reactive, because it's called the dipole force, because it looks like it is due to the dipole momentum potential. there is some algebra to do, and we actually recover this formula here. So this formula here is proportional to h bar omega squared divided by 4 delta, which is exactly the shift of the Hamiltonian, the perturbed Hamiltonian, in the case if we add the electromagnetic wave in the rotation in the rotating wave approximation. This is the very famous AC star shift of the Bayer atomic system that we, as metrologists, always look and measure. But if there is also a spatial dependence on this shift, we also get a dipole potential that we can use, for instance, for trapping particles. Also, we have to look at this formula. There is a very different dependence on the detuning from the resonance. Okay, we already mentioned, for instance, when we looked at the interaction with the vacuum electromagnetic field reservoir, this system is actually subject to fluctuation. And in fact, we always take time and spatial averages, but actually there are a lot of, we can see that if we look carefully at the trajectory, there is like a Brownian motion going on in the dynamics of the single atom. So we can write down an equation for the spread of the momentum of the atom, which can be parameterized by this diffusion parameter d spontaneous. And this is due to the fluctuation of the spontaneous emission process, which is proportional, of course, to the single step amplitude, which is, of course, h bar k, the rate at which it happens, and which is proportional to gamma times the usual rho EE stationary value times t. From this equation, we can derive an expression for the spontaneous emission diffusion, and again, we have this Lorentzian dependence. The same happens also if we look at the number of photons that we absorb, and if we do the same calculation, we get almost the same order of magnitude. So if we believe it is a Poissonian distribution process, it is exactly the same. Otherwise, there is a correction for the statistics of the absorption. But we can take twice this t as the spread of the momentum, and we call this as the rate of heating of the system due to the interaction with the light. This is more or less what I wanted to say about the mean radiation, light radiation process. So it was in more or less 45 minutes. So do you have other questions? Okay, we can go quickly to what follows. So for now on, we just calculated the effect of the force on the system, but we didn't demonstrate that we can take a bunch of atoms and cool down their statistical distribution. And actually, if we just take one beam, one single beam, it is not possible to cool the atoms down to rest. Of course, there is some point in which the atom will reach a minimum velocity and then it will go backwards. So the way to do Doppler, to do laser cooling, is to use two counterpropagating lights in such a way the atom can feel in both directions the effect of the radiation, the light interaction. In the case, how do we deal with the dynamical problem of a moving atom? Simple. We use the Doppler effect. Simple. In the limit of small velocity, we just recover the stationary problem, and we shift the frequency seen by the atom by the Doppler shift. And we can see that if we have two laser beams non-interfering in the, let's say, low intensity limit, they cancel out their force at 0. So it is possible to get a viscous force that is always counter-propagating with respect to the velocity direction of the atom. And of course, this requires that the detuning of the atom is negative. And looking back at the Bloch equation, we can extrapolate a friction factor which is proportional to the, in the low intensity limit, to the saturation parameter. So how do we get the ultimate temperature in this system? We do the derivative of the momentum using this very simple formula, which is just a minus alpha over m times p. From this we can get how much of distribution, so delta p squared evolves, and this is simply alpha squared over m plus delta p. So this is in principle an equation that goes to 0. Of course, this is not possible because, as we mentioned before, there is an heating mechanism going forward. So the equilibrium temperature is reached when the heating and the cooling mechanism cancel each other out. Of course, fortunately for the heating system, there is no direct dependence on delta P, so it is possible to express at equilibrium temperature that in the low energy limit has this simple formula. So there is a term that increases with the detuning and another term that decreases with the detuning and gets this very nice V shape with a minimum that is reached easily at gamma over 2. And again, we recover the limit of the Doppler cooling, which is h bar gamma over 2. Again, is exactly the same formula that we already know from order of magnitude calculation, except for this 1/2 term. If we take some typical example for strontium and for the strong strontium transition, the Doppler temperature limit is very high, is about 700 microkelvin. For the rubidium one is much less, is 140 microkelvin, but is still quite high. And in fact, when Bill Phillips and Stephen Chu and others started to measure the limit of very low intensities and try to confirm the Doppler theory, they saw this very typical figure. This is for sodium. And this is very, very different. Both the behavior with respect to the detuning and the position of the minimum and the absolute value of the minimum with respect to the Doppler theory. So it seems the Doppler theory is really like a toy tool and doesn't work very well. And it is, because when we made all these calculations, we forgot a lot of things. For instance, it never happens that an atom is completely with two-level systems. And for the alkali systems, actually, this is completely not true. And the interaction of the polarization gradients that we completely forgot here with this multi-level system get rise to some sub-Doppler mechanism that gives this low temperature limit. This is for sodium. Sodium has a Doppler temperature of 240 microkelvin, and this is about 40 microkelvin, which is exactly the other temperature that is important in this problem, which is the temperature associated to the recoil energy, which is typically smaller than the Doppler temperature because of the broadband approximation that we made. But this is also not an ultimate limit too. It is possible, and maybe you will see in the next lecture, to overcome this limit. There is an atom that is quite similar to at a very good approximation, is like a two-level system, and is the strontium atom. So at least one expects that we see this 700 microkelvin. Unfortunately, I didn't have time to include the picture, so I just draw here. Do you see? So all the equations I wrote, they can be scaled because they're all, the detuning is parameterized by the gamma, so we can always write these kind of plots that are universal. So if this is our Doppler limit, this is what in strontium we typically observe. We see almost an order of magnitude higher temperature than the Doppler limit. And this is still even more surprising what's going on. And this is because when we made this approximation, we have to be sure that the two beams do not interfere at all. If there are some intensity gradients, there can be some mechanism that start to induce heating. And this is what typically happens for strontium. Probably because strontium has this very big scattering rate. This is very, very inclined to have this very, very high temperature. And this is also a measurement done by another Nobel Prize, Jan Hall. So it's still a Nobel Prize work, but not something to be proud of. Okay. So with the 3D optical molasses, we can take atoms from a vapor, from a beam, from wherever we want. And the coldest part of the atoms will start to feel the interaction with the 3D molasses and will accumulate toward the center. Actually not, because as we said, there is no confinement in these dynamics. So they will start to cool and then will escape from the cooling region. So we need to find, if we want to make a clock, for instance, we want to know exactly the position of the clock, interrogate the atoms always at the same place. We need to find a way to, let's say, trap exactly the atoms in one position. And this was done by Stephen Chu and co-workers by adding a position-dependent Zeeman shift. How do we do this? We put, this is, for instance, a one-dimensional system. We put a magnetic field gradient. For parity, I never said, but we cannot have a j equals 0, j equals 0 transition. Typically, we need at least delta L equal 1. So the excited state typically has at least j equal 1. So it has some Zeeman sublevels. And in presence of a gradient, they split in function, as a function of the position. And then we just modify our optical molasses with two circularly polarized light. And we see from the Zeeman splitting that typically, for instance, if the atom is in this position, it will be more inclined to absorb the light from the sigma plus less than the sigma minus that is completely out of resonance, because for sigma transition you have to you need a delta m equal plus minus 1 in the Zeeman sublevel quantum number. So adding this feature, we also can derive a elastic force, where at the first order approximation is proportional to our viscous force times the difference of the two magnetic factors, magnetic moments. And this is very typical because the ground state typically has something like j equals 0. And instead, we usually do laser cooling with something like j equal 1, but L equal 1 or more. So there are very different Landau factors, and so this applies very well. Again, this is not true for strontium, but this time strontium-87. Since if we look cool at the intercombination transition, more or less the splitting of the two is the same. And actually there are, for some Zeeman sublevel, that they have the same probability to absorb sigma minus or sigma plus. And basically there is no confinement at all if we use just one single laser. How do we realize experimentally this configuration? If we want to make a 3D confinement, the straightforward solution is to take a pair of coils. We drive the same current with anti-Helmholtz configuration, and we get, for the Maxwell equation, a very nice quadruple field with the gradient on the zeta direction twice the one in the x and y direction. And with the proper circular polarization, we get a lot of atoms at the center of our trap. But we can also exploit a quadrupolar magnetic field also in one single direction. If we take some squared coils with one dimension much bigger than the other, at the center there is like a zero field. And this can be used, for instance, not for trapping, but as an atomic funnel. So if we have some atomic vapor or a beam coming from a transverse direction, they will be funneled in the zero force point and escape if there is a push beam can be directed wherever we want, in particular on, for instance, another 3D mod. Okay, this is something that I want to advertise, but also think about a little bit better. So when we look at trapping, of course, we want just to maximize the force. We are not so interested on finding the lowest temperature possible. And this is related also to the so-called capture velocity. So for a given force, there are some velocity classes that if we integrate the equation of motion, at the end are confined or are just escaping. And as we said before, the Doppler cooling force has a very severe limitation. The amplitude cannot overcome the maximum value. And also, to increase the capture range, in principle, we could broaden the resonance by just adding more power, but this broadening is not very efficient because of the square root dependence. So something that we and Matteo studied last year is, instead of wasting a lot of power just on a single frequency, optimize to maximize the capture of our, in this case, 2D mod, we split the power available on two different frequencies in order to have already some velocity classes that are resonant with a far detuned part of the radiation. And maybe this can fall inside the capture range of the standard cooling beams and increase the overall capture rate. This has also another beneficial effect that I don't know if I will mention later. So I will go back to this later. So we didn't speak about the second part, how to use the second part of the light force, and because typically the dissipative part is much bigger than the dipole part, and this is completely absent on resonance and if there is no field gradient. But there are some conditions of the detuning at which we can suppress the dissipative part and we can emphasize the conservative dipolar force. So if we increase enough the detuning, we can decrease this ratio, we can increase this ratio at will and make so very good conservative traps for even for neutral atoms. And this is because of the different dependence on the detuning that I probably forgot to mention. In fact, the dissipative part has a square dependence on the tuning from the resonance. Instead, the dipole part is inverse dependent on the detuning. So at far detuning distances, the dissipative part can be cancelled out, and only the dipolar force remains. And this we can exploit also in the consideration of our enhanced trapping system. So the farther you go from the resonance, the lower is the scattering rate. And since at the end the atoms will stay basically at the center, they will feel less power, less scattering power in the configuration of two frequencies with respect to the one frequency. And this means that if we make, for instance, as we did, an atomic beam in a 2D MOT, this will have a thermodynamic temperature a little bit smaller than for the standard case. And this is what we observed. So we increase, for instance, the loading of a 3D MOT, not just because we capture more atoms, but also because the divergence is less, so it's more directed and is more efficient, the loading. So fortunately, we always work with Gaussian beams that provide a 3D gradient to trap the neutral atoms. And we can use lasers in several ways, just a single focus beam, two crossed beam, or in the standing wave configuration. The other ingredient to increase the force is, of course, the length of the gradient. And if we look at the Gaussian beam, the typical length scale for the focus beam is, in the radial direction, the size of the waist. Instead, which is inversely proportional, which is proportional to in the axial direction to the Rayleigh range, but is still much less than WT of the waist. So a way to increase dramatically this dipole force is to tightly confine at the level of half of the wavelength of our radiation in the standing wave configuration. In this configuration, we really get very strong forces, and actually you cannot treat the motion in this direction classically, but you need to really solve the quantized problem. And this is very important for optical lattices, as you will see later in the school. I want to remark just that anyway, when we use this kind of systems, these are still very shallow traps. And typically, we need at least a temperature of the order of 1 microkelvin. And typically, a simple Doppler cooling on a broadband transition doesn't work to load efficiently these traps. Okay, we have basically all the ingredient to make an ultra-cold optical clock. So what is remaining to deal with is how to build an atomic source, and if it needed to make a slowing of our beam, and then try to circumvent the problem related to the final temperature of Doppler cooling, for instance, using a narrow line width transition with broadband cooling and then narrow line width cooling. Then exploit the quantized motion inside the optical lattice, and there is the so-called sideband cooling. And then we want to also measure the temperature and all the thermodynamics of the system, so we need to develop imaging and detection techniques. But for this and for other schemes like sub-Doppler, Bose-Fermi gases, and more, I leave the problem to our next tutor, Florian Scheck. Thank you.